A Fourier series. This is a review. I will only teach what's really necessary to understand, be possible to use in power electronics. It's used for steady state periodic waveforms. What's the meaning? If I have a function y of t, ever capital T, which is called period, it's the same. There's a repetition of values, ever capital T. T is the period, or the inverse of the frequency. We can also associate T with the angular frequency, omega. T is 2 pi divided by omega, or omega could come here. Omega is 2 pi divided by T, and 1 divided by T is F, frequency, so omega is 2 pi F. If a function is distorted but periodic, we can have an expansion. That expansion was proposed by a French mathematician called Joseph Fourier. We can see here how is that expansion. I can take this periodic function and make a substitution by this. Y of t is given by a coefficient a sub 0 plus an infinite summation from n running from 1 to infinite of brackets, two things that will be added, a cosine and a sine. So for n equal 1, I have a1 cosine of omega t plus b1 sine of omega t. When n is equal to, I have a2 cosine of 2 omega t, b2 sine of 2 omega t. So we can see here that we have coefficients for my cosines, coefficients for my sines. The coefficients, they are associated to the n, and n we call the harmonic. When n is equal 1, I have omega t, and omega t is the fundamental. So when n is equal 1 is the fundamental. When n is equal 2, I have 2 omega, that means twice the fundamental. When n is equal 3 is 3 omega, is 3 times the fundamental, and so on and so forth. And what's a naught? A naught, there is no sine, there is no cosine, it's a number, it's a real number. We can associate this in electrical engineering as a DC value. So what I have is my function that's steady state in periodic and distorted has an expansion given by a DC value plus a sum of harmonics. If you go back to trigonometry and you take a sine and a cosine, you can associate the sine and a cosine into another sine or another cosine. In this case here, I'm associated with another sine. So I'm taking these two ones here and I'm combining in a new formulation where instead of a1 cosine of omega t plus b1 sine of omega t, I'm going to have for that particular harmonic square root of a1 squared plus b1 squared. That's the peak value or magnitude of that first harmonic, multiplied by a sine, could also be a cosine. Sometimes you see a Fourier expansion in terms of cosines. In this case here, I'm showing sines. A sine of same harmonic plus a phase. The phase is the inverse tan of this coefficient divided by that coefficient. We call this Cartesian formulation. Why Cartesian formulation? Because I have cosine and a sine, they are orthogonal functions. And I call this a polar form. And a polar form sometimes is discussing math as this formulation here. E angle, CNEJ alpha or phi or theta. We call this Euler's expansion. Why? Because this is the exponential, the natural logarithm, the natural e into a certain exponent. This is given by cosine of that plus j sine of that. So pretty much this exponent will come back to here. So this exponent will easily come back to the Cartesian form or rectangular form by the Euler's formulation. And then we can come back here. So they are related. So the polar form could be given by this way or by that way. The Fourier coefficients, they are calculated with integrals. How do you do those integrals? Take a piece of paper, okay? Take a pen, write your equation and solve it by hand. That's a way to do it. There are other ways to do it, of course. You can use a symbolic software. You could use Mathematica. I think you have access to Mathematica at the University of Denver. You could use Maple. Maple is another software that's symbolic. There is a software called Sage, S-A-G-E, is symbolic. And maybe there are some other symbolic engines. The most typical ones are either Mathematica or Maple. Or you just do it by hand. Here, we are trying to pre-calculate a few Fourier expansions, and I hope you can understand how they work. So the Fourier coefficients, they are calculated like this. The first one is the average, see, A naught is pretty much the average, see, 1 divided by t, integral of t, y of t. That's the definition of average, DC value. So whatever comes here is the average of the function. N and Bn are the coefficients like here. N is the coefficient of cosine, and Bn is the coefficient for sine. So An, you take your original function and you make an integral of cosine. Why? Because An is the coefficient of cosine. And Bn, you take this integral of the original function and make the integral with sine. So you multiply it. That's a multiplication. You take your original function, multiply by cosine, and then depending on the harmonic, you do integral one at a time. For example, suppose you want to calculate for the first harmonic. So n is equal 1, that means cosine of omega t. So A1 is 2 divided by t, integral in one period of y of t multiplied by cosine of omega t dt. And this is t. This is in time. This is in time. It's not in omega. B is the same. B1 is the same, similar, but then it's sine. If I want to calculate for A7, A7 is the seventh harmonic. So A sub 7 is 2 divided by t, integral in one time period of the original function multiplied by cosine of 7 omega t. B7, 2 divided by t there, y of t, sine of 7 omega t. So for each harmonic, you have to calculate two integrals. One to calculate An, another one to calculate Bn. And after you calculate An and Bn, you can build your polar form. So the polar form also needs you to find the coefficients of the Cartesian form. So the easiest way is do the Cartesian form and then go to the polar form. I suggest you to take a look in a book, maybe Applied Math or maybe an Electrical Circuits. Old books, they used to have this discussion. Today, they usually give you a table or some simple discussions. So review an Applied Math book or an Electrical Circuits book to understand how to calculate Fourier coefficients. Just to understand, and I'm not going to ask you to do this in your exam, but you need to understand how they work. When you have even function symmetry or odd function symmetry or half wave symmetry, you just calculate, for example, the sine coefficients or only the cosine coefficients, or sometimes the coefficients are related and symmetrical. So depending on the symmetry of your time domain function, you don't calculate all the coefficients. Those features will help you to calculate by hand. For example, let's say I have a square wave. As long as we have a mathematical formulation for the periodic steady state function, we can calculate all ANs and BNs. Here I'm saying AI and BI. Sometimes I mix coefficients. In the previous slide, I was saying N, and here I'm saying I. But eventually be A1, B1, A2, B2, A3, B3, first harmonic, second harmonic, third harmonic. Let's say I want to find just the first harmonic and not the whole series for a square wave. So first, a square wave is symmetrical along the vertical axis, isn't it? See, that's the vertical axis. This is opposite to that. If you move t divided by 2, this is negative, the other is positive. So we call this odd function. Odd function, that means y of t is equal to minus y of minus t. An even function is y of t is equal to y of minus t. Suppose a v, letter v. One side you have a slope that's positive, another is negative. So that is an even function. An odd function is, if you look to the right side of the horizontal, the vertical axis, you have to make it negative and flip it, so it becomes an odd function, symmetry. So in this case, we don't have cosine terms. Well, it's very simple to see this, even though we make a big deal about this symmetry. See, if you look here, it's very easy to match a sine. Look, see, a sine starts at 0, goes up and down, goes down and up, so it's synchronized. So in a function like this, I can easily match sine. So I just need to calculate the sine coefficients. There are no cosine terms. And I want to find the first harmonic. So what I do? Well, A1 is 0 because we don't have cosines. I just have to find for B1. So B1 is calculated by this integral. I do the integral with sine. And I of t, well, for the first half is a positive value. For the second half is a negative value, isn't it? That's what's happening here. See, I peak minus I peak. So that's what I did here. I peak minus I peak. But the sign is still there. So I make all the substitutions in alpha because it's easier to integrate in alpha. So I have sine of theta, d theta, integral from 0 to pi, pi to 2 pi, and then I have divided by 1 divided by pi. So when you do this, you just do it by hand, and you see that B1 is 4 times I peak divided by pi. So that's the coefficient for the fundamental. So the expansion will be, the fundamental will be 4 I peak divided by pi sine of omega t. So if anybody gives you a square wave and asks what's the fundamental for that, that is the value. What's the RMS of the fundamental? Well, is this here, this coefficient, divided by square root of 2. If you do for all the other terms, you can do it. So you have a series. So I can have an expansion, but because there are symmetries here, we do not have the odd harmonics. First, In this case, I do not have the cosines. Second, I do not have the even harmonics. I only have the odd harmonics. So I have the harmonic number 1, 3, 5, 7. I only have the odd harmonics. So I have a summation of n from 1 to infinite, but only for the odd harmonics, 1, 3, 5, 7, 9, 11, so on and so forth, of this calculation here, only the odd harmonics. So a square wave is an odd function like this, is simple to calculate. I can also take my vertical axis and move along here, that's centralized here, and then I have a cosine expansion, which is the same. You just calculate for the cosines, the sines will be 0, and it'll be similar. So any non-sinusoidal periodic waveform, that means you have a waveform that repeats with a certain angular frequency omega, would be expressed in a infinite sum. And we have two possible configurations. One is a summation of sines and cosines. Another one is a summation of sines with a certain magnitude and a phase shift. Because when you do the rectangular form, the sines and cosines, if you go back here, see, there is no phase shift here. But when you do the polar form, then there is a phase shift, because that phase shift depends on the coefficients of your Cartesian form. When we do Fourier series, we can do a mathematical approach, and we can try to find a closed formula. What's a closed formula? It's a formula that works for the harmonic from n equal 1 to infinite. So that's a closed formula. But sometimes we do not find a closed formula because we're not mathematicians. Mathematicians love this series and closed formulas. So what engineers do, they will do like this. I have this waveform, and the harmonics usually decay the magnitude. So we truncate the harmonics series. So we calculate for the first 10 harmonics. Okay, and then we stop. Then you say, well, it's not precise. No, it's not precise. It's a simplification. But in engineering, you do a lot of simplifications. Sometimes a simplification is a very good solution, and a very precise calculation is not feasible because it's too complicated to achieve. So for electrical engineering applications, usually a formula is truncated. That means you solve for the harmonics and then you stop. You could solve by hand. You could solve using a software that helps you do scientific analysis. For example, MATLAB. MATLAB is not for symbolic applications, unless you use the symbolic toolbox. But MATLAB is for calculations. So I could have a sine, and I could use an integration for that sine multiplied by something and calculate that coefficient. That's possible to do it. I can do several calculations using what we call a simplified way to implement the integrations. If you did numerical analysis before, you know that when you have any function, you can make an approximation of a segment of that function by a straight line approximation. So you can calculate the area of that, and that's a trapezoid. So we call trapezoidal rule or Euler's rule for integration. So we can do that. We could do that numerically for, I don't know, 10 harmonics. Here we're saying 20. And when you do this, we stop and say, well, I just calculate for the 20 harmonics, and that's what I'm going to use for my calculation. So that's the Cartesian form. And that's the way we do polar form. And the polar form, look here, coming back here. The polar form, it's a certain magnitude. Sine could be also a cosine, the frequency and a phase shift. If I plot the magnitude and the phase shift as I change omega from 1, 2, 3, 4, 5, we have a plot where in the horizontal axis we have frequency, could be in omega, in radians per second, or could be in hertz. And then I can have two plots. One is the magnitude, another is the phase shift. We call that frequency response. And it's very important, this frequency response, for control systems, for analysis of filters, design of filters. So that's what we do. We do the Fourier expansion, and then we plot the harmonics in terms of the magnitude and phase as we change the frequency. Here I took some page from books and notes. It's mixed, but I tried to put in these lecture notes most of the important waveforms that we use in power electronics. So there is a definition here. Actually, this came from the book that I list as a textbook. Is the Power Electronics book by Haidt, H-A-I-Y-T. The back of the book, there is appendix on Fourier. So here you see, so that's the Fourier expansion for a half-wave rectifier. See, I have here the harmonics and the DC value. Then I have for the full wave, we have here. This is something important to learn next week. If I have a three-phase rectifier with 6 diodes, I have 6 poles. So I have this Fourier expansion. There is a DC value here. There is a Fourier expansion for the three-phase bridge rectifier. Post is always important because in power electronics, we always have switches on and off. So here you see that there is a voltage, okay, VM, and then it goes to 0, and then it repeats. So there is a period here, T. There is a fraction of that period, dt. dt is a duty cycle, a number between 0 and 1. So let's say that's 0.2 t or 0.3 t, okay? D is the duty cycle. So here is the average of that, coefficient for AN, coefficient for CN, BN, and this will be the polar form. Square wave, we just discussed, we did that by hand for the fundamental, so that's the expansion for the square wave. This is another post that we usually use in power electronics. It's important also for three-phase rectifiers. Here there is a parametrization. Suppose this is alpha from 0 to here, and it's symmetrical. This is pi. So this is pi minus alpha, pi plus alpha. So it's all symmetrical. So for this particular, we call modified square wave, because it's not really a square wave. It's a pulse centered at pi divided by 2 with a certain width, and it's the same, the positive and the negative, symmetrical. We could even parameterize this another way. See, if this is alpha and this is alpha, from here to here is pi minus 2 alpha. So you could say that's wide as pi minus 2 alpha. But why you have this parameterization? Because that's what the way that was calculated Fourier expansion. And we have here the expansion. Another one that's important for power electronics, when you have a 6-step, we have inverters that we switch on a transistor one at a time. We also call this quote unquote cake wave. Why cake? Because it looks like a cake. See? Could be a wedding cake. There are several steps here for your cake. So there is one step, then there's another step, then it comes down, then goes negative. So for this 3-phase 6-step wave inverter, why 6-step? Because see, 1 and 2 and 3 and 4 and 5 and 6 and then it repeats. So I have 6 steps in one cycle. Okay. We have the expansion here. I also have Fourier expansion of line to line voltage. So this is a handout. The previous page were from the back of the book. These are some handouts I have in my binder. So if I have an inverter like this and I have this 6-step wave, I can build the line to line voltage. So when you do this, you have this Fourier expansion. We can talk about this when we discuss inverters. Then there's a table here. Maybe there is a repetition of a few things because see, this is similar to the previous one, but this is kind of parameterized because that was alpha, but here is pi divided by 3. So this is not exactly as general as alpha. I'm saying that's symmetrical here, and this is defined as pi divided by 3, and pi divided by 3 here is centered as around 0. So that's the Fourier expansion. That's the Fourier expansion for this pulse. So depending on the pulse, depends on how you make the timing and steps, you're going to have a different Fourier expansion. Why this is important? Because this will be studied in next class. If you have a full wave rectifier, you have this voltage waveform. And if that voltage waveform is applied to R and L, that means from here to here, I have a full wave voltage. However, if your inductor is very high, you're going to filter, and I naught will not be pulsed, will be an average value with a certain AC. So that's what happens with I naught. Look, see I naught here? That's I naught. I naught has a certain fluctuation with a certain AC we call ripple. Ripple is a variation, and a DC. So I can size my inductor depending on how the Fourier expansion here will give me a current. That's what we're going to do next class. For a 3-phase rectifier, if I size my inductor to have a very constant current, we'll see later that in each phase, you're going to have this kind of current waveform. So I can have the Fourier expansion, and I can do something that I will discuss in the week after that. We'll have what we call power factor. So why Fourier series are important? Because you can define a harmonic expansion for your voltage or for your current. And then by using an equivalent circuit, what's the equivalent circuit? I have here a distorted voltage. The distorted voltage is composed of harmonics. Let's say fundamental, third harmonic, fifth harmonic, and seventh harmonic. So fundamental, third harmonic, fifth harmonic, and seventh harmonic. So I have to calculate 4. What I do is, because my system is linear, I can say that by superposition, I could solve my circuit for the fundamental, for the third harmonic, fifth, and seventh harmonic. I take the values using a phasor analysis. Phasor analysis means complex numbers. And then I'll add them together to formulate my total response. I will be doing that next class. In class exercise, discuss in your group how a steady state periodic voltage source, non-sinusoidal, such as a square wave, could be a rectangular wave, or a pulsed wave, or a sawtooth, or maybe a sinusoid of distortion. Maybe it's sine, but it's clipped. Maybe it's sine with peak and oscillation and coming back. Maybe it's sine, but across zero crossing, there is a little bit of distortion we call notches. Let's say that this voltage source is feeding a load, and the load is RL. That means resistance plus inductance. And I want you to model as an equivalent circuit how we can make a solution for calculating the current through RL. I want you to define how is the total current with the Fourier expansion. Then I want you to define how you can calculate the total RMS of this current. And I want you to define how you can calculate the RMS of the fundamental of this current. A Fourier expansion is a sum of harmonics. So let's say that your voltage source is a ramp, a sawtooth goes up, comes to zero, goes up, reset, sawtooth. So let's say that, well, this is not sine wave. So what should I do? I know that's a sum of sine waves. So that sawtooth will have A1 sine of omega t plus phase for first harmonic, A2 sine of 2 omega t plus another phase for second harmonic. So you can do this for each harmonic. So let's say that your sawtooth you want to represent with 5 harmonics. So you have a sine for the first, sine for the second, third, fourth, and fifth. It's a sum. So you could imagine, just imagine that you have a series connection of V1 plus V2 plus V3 plus V4 plus V5 is a string of voltage. So you're replacing the sawtooth with a string of 5 series connected equivalent voltage source. And then you have RNL. By theorem that you learn in linear circuits called superposition, what you do? You take one effect at a time. So V1, and you short all that, and then you have an equivalent circuit. How you find that equivalent circuit response? Using phasor analysis. So you take V1, you take the phasor form, J omega, and then you have R and the J omega for the first, and then you calculate. And then you short that, you go to the next one, is V2. So you have V2 short, short. So you have another component, which is V2, which is 2 omega. So you have another circuit where you have twice the frequency. So you find that for the twice of the frequency. And then you go for the next one. You calculate for 3 omega, 5 omega, 7 omega. So you find all those responses. And then you go back to the original problem, which is the string. And then you sum of those. So that's what we do to find the best filter for a rectifier. A rectifier, let's say a full wave rectifier. A full wave rectifier has a positive semi-cycle, and then the negative semi-cycle also becomes positive. You have that. So I have a Fourier expansion. So if I want to find a good filter, I will find an inductance that will decrease the current that will follow in your circuit, where you have a very high average and maybe second harmonic, but you attenuate all the other ones. So that's what I'm going to do. I start with a very simple discussion like we just did right now. I will apply for a full wave rectifier. The full wave doesn't matter if it's center tap or diode bridge, it's the same way you calculate the filter. And then I will discuss how that can be extrapolated for a 3-phase. So I have to teach 3-phase. And then I will show you that instead of inductor, if I have a capacitor, what I have to do. So pretty much that's what I'll be doing in the next lectures. How to design capacitors and inductors for those rectifiers.